So now that the Higgs particle has been done and dusted, it's time to think about what comes next for fundamental physics. And I think one of the major stories in the coming years is going to be about dark matter. This is one of the most profound questions that physicists are currently facing. We have to infer that there is such a thing as dark matter in the universe, but we have no idea what it might be. The idea of its existence stemmed initially from a realization in the 1930s that rotating galaxies ought to fly apart unless there was some other kind of gravitational attraction holding it together beyond what could be accounted for by the visible matter within the galaxies. But there was no sign of what this matter might be. It seemed to be something that, although it had gravitational effects, it didn't really otherwise interact with ordinary matter or with light or any other sort of electromagnetic radiation at all. And this is why it's said to be dark. Over the intervening decades, plenty of ideas have been put forward for what dark matter might be, but I think it's still fair to say that all of them are really just guesses. However, in recent years, there have been several experiments set up to try to detect some of the hypothetical particles that have been put forward as candidates for dark matter. One of the favourite ideas is that these particles might be so-called WIMPs. That stands for weakly interacting massive particles. And that name always seems to me to be pretty much a restatement of the whole notion of dark matter. These particles are massive, they have gravitational effects, but they are weakly interacting. They barely interact at all with ordinary matter. However, it's that barely that is the crucial part of the equation, because the hope is that just occasionally, very rarely, one of these particles, one of these dark matter particles, can collide with a particle of ordinary matter, and that the effects of it will therefore be observable. In particular, what should happen is that if a dark matter particle collides with an atom, it will cause the atom to emit a characteristic kind of light, which ought to be capable of being detected in highly sensitive detectors. So this is basically what most dark matter searches are hoping to find. These are experiments that have to be conducted, on the whole, far underground, because they have to be sheltered from any other background radiation that might cause similar effects, and in particular from the effects of the collision of cosmic rays. And so many of them are housed in deep mine shafts, a kilometre or more underground, where pretty much all of the cosmic rays will be shielded out. Now, just this month in October, one of the key experiments of this sort, in fact the most sensitive of these experiments, an experiment called LUX, being conducted in South Dakota, reported the results of its first 3 months of running. And what it found was nothing. So that doesn't seem like big news at all, and in a way it isn't, and in a way it's no great surprise. But what it does tell us is that some of the previous experiments that have looked for dark matter and that have sometimes seen events that seem to be hard to explain in any other way, that seem to be possible telltale signatures of dark matter, that these possibilities seem now to be ruled out. That if those experiments had seen them, then LUX certainly should have done. LUX consists essentially of a cylinder of liquid xenon, within which collisions between a dark matter particle and the xenon atoms should create this light emission that light detectors around the cylinder would then spot. Now, as well as ruling out the possibility that previous experiments might have seen dark matter events, the null result at LUX also helps at least to constrain where we might look for dark matter. It shows that it's, if you like, there's no point in looking here, we have to look there, we have to look at these energies. LUX is going to continue running throughout 2014 and 2015. And so are several other dark matter experiments underway. One of them, called the Alpha Magnetic Spectrometer, or AMS instrument, is running on board the International Space Station. And this looks for dark matter in a slightly different way. It looks for the antimatter particles, the positrons, that should be created if two dark matter particles, if two of these WIMPs collide and annihilate one another in space. And the AMS experiment, too, earlier this year in April, reported some findings that, while not by any means suggesting that it had found dark matter, nevertheless seemed to be anomalous, seemed to be slightly hard to explain, although it certainly was possible that they might have more mundane explanations, such as coming from particles emitted by pulsars. And it now seems, in the light of LUX, that this is indeed the most probable explanation. So in a sense, we're back to the drawing board. However, there is a fair bit of potential for that to change in the coming years, and one of the most enticing possibilities is that the particle collisions at the Large Hadron Collider at CERN might actually produce some of these hypothetical particles of dark matter. However, it's also possible that we may in the end be forced to conclude that dark matter doesn't exist at all, that actually what we've taken to be dark matter is actually the manifestation of some other physical phenomenon or force beyond any that we know so far. Here's where you can get more information about some of the current dark matter projects.